Hi, I'm Sarah, and my science experiment is water rockets. The main research project is explosives. While studying this topic, I've discovered that the definition of explosion is a release of energy. The release can be slow, like a gunpowder fuse, or fast, like dynamite. It can be chemical, like TNT, or physical, like a pressure cooker that breaks, causing a sudden release of the air. Because of the danger of normal explosives, I need to select something for my experiment that was safe, but still gave the general idea. So I picked water rockets. Water rockets use air pressure and water to fly. They're made using an empty soda bottle, water, and air from a bicycle pump. Fins are added to the bottle to help with stability, and a tennis ball is attached at the top for a cushioned landing. A small amount of water is poured into the bottle. Then the bottle is placed onto a launch mechanism, which is airtight. A bicycle pump is attached to the launcher. And air is pumped into the bottle. We use a gauge to show how much air pressure was being used for each launch. After the rocket is pressurized, we use a bicycle brake cable to open the valve under the rocket. This releases the pressure, or potential energy, and it becomes kinetic energy. The result is a physical explosion, which is controlled and directed through a small opening or nozzle under the rocket. As the compressed air pushes the water down, it lifts the rocket up. I did 2 experiments. In the first experiment, we performed several launches using the same bottle but different pressures. So the independent variable is pressure in pounds per square inch, or PSI, and the dependent variable is apogee, which is just a fancy word for how high the rocket flew. The air pressure was varied from 10 psi to 60 psi, in increments of 5 psi. The control variables would be the volume of the rocket and water used, since it was the same bottle each time and the same amount of water. The predicted hypothesis was that more air pressure would cause the rocket to fly higher, which proved to be correct. We videoed each flight and used a 10-foot pole on the ground as a reference point to measure the rocket's height. This measuring system wasn't perfect, because if the wind caused the rocket to drift significantly closer to or from the camera, the position of the rocket at apogee could become exaggerated. This became especially problematic as the flights went increasingly higher and the camera angles got wider. This graph shows the air pressure for each flight and the measured apogee, or maximum height, that the rocket reached. The measurements from 10 to 45 psi appeared to be reasonably accurate, but the wind and camera angle made measurements above 45 psi difficult to record accurately. So the data on those flights may only be a rough estimate of what the expected alpages should have been. The second experiment used bottles of different volumes or sizes, but the same pressure. So the independent variable was the bottle size, and the dependent variable was, again, the apogee, or height. The control variable was pressure, which remained a constant at 30 psi. The predicted hypothesis was that smaller bottles would fly higher because they were lighter. This proved to be false, however. It turns out that because the bigger bottles could hold more air at the same pressure, they had more energy to lift, even though the bottles were slightly heavier. These flights were short and filmed very near the measuring pole, so the measured distances were more accurate than the higher flights in the first experiment. This graph shows the volume of the bottles used for each flight and the apogee, or maximum height, that the rocket reached. Thanks for watching. I had fun doing this project. Well, until next time. Goodbye!